Welcome to NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California. I'm Guy Webster with the JPL News team. 11 years ago, NASA's twin Mars Exploration Rovers didn't yet have the names Spirit and Opportunity. They were right here, 2 buildings east of this auditorium in JPL's spacecraft assembly facility. Exactly 10 years ago, tomorrow evening, 2 buildings north of here, the control room team celebrated boisterously on getting the signal that Opportunity had landed safely on Mars. Spirit had been working for 3 weeks already at that point, and Opportunity was ready to begin a mission that was scheduled to last for just 3 months. Spirit, lasted 6 years, kept working for 6 years. In 2012, NASA sent a bigger Mars rover, Curiosity, reached Mars. 10 years after Opportunity's landing, Opportunity is still working on Mars very productively. I'm going to introduce you to 4 panelists who will be telling you about a decade of roving on Mars, and in particular, some important new results being published in the journal Science tomorrow. Two of the presenters are here at JPL. Ray Arvidson of Washington University in St. Louis is the Deputy Principal Investigator for the Mars Exploration Rovers, Spirit and Opportunity. He's also the lead author for the research report that you'll hear about. John Callas of JPL is the project manager for the Mars Exploration Rovers. And 2 of today's presenters are joining us from the television studio at NASA's Goddard Space Flight Center in Greenbelt, Maryland. They will be the first and the last in the order of presentation, and you will hear from Michael Meyer of NASA's headquarters in Washington, D.C. He's the lead scientist for NASA's Mars Exploration Program, which includes several missions at Mars and in development. Steve Squyres of Cornell University in Ithaca, New York, is the principal investigator for the Mars Exploration Rovers. After all 4 presentations, we'll have plenty of time for questions and answers, so let's stay at Goddard Space Flight Center and hear from Michael Meyer.
Well, thank you, Guy. It will be 10 years ago tomorrow that the Mars Exploration Rover Opportunity landed on the surface of Mars. And to kind of relive that excitement, we have a video showing the rover going to the surface. So if we roll that video, we can see the capsule entering the Mars atmosphere. It will slowly unpack, deploy airbags, and then bounce several times on the surface before actually coming to a halt and landing. But the real payoff from this mission started on the day that Opportunity landed. It began science operations that lasted over 10 years, 9.75 years beyond the rover's warranty. We are here to celebrate the 10th anniversary, but more importantly, 10 years of groundbreaking research that is exemplified in the paper that is published coming out this week in Science magazine. The bottom line is, we have discovered another place on Mars that could have provided a habitat for life in a more ancient time. This paper also highlights the importance of the Mars program in which we have landed assets and orbital assets on Mars that have played an important synergistic role. For instance, for Opportunity, Mars Global Surveyor and Mars Odyssey identified Opportunity's landing site, finding hematite, which is an aqueous mineral, which became known as blueberries. Both Odyssey and the Mars Reconnaissance Orbiter provide telecommunications between Mars and Earth. The high-resolution camera on the Mars Reconnaissance Orbiter provided strategic navigation information for the extended mission. And the infrared spectral imaging on the Mars Reconnaissance Orbiter, XRISM, has identified the clay minerals that were studied by Opportunity that are published in this issue of Science. It has been this Mars program, the logical sequence of missions, that have brought us to this point. By standing on the solar panels of Spirit and Opportunity, we see the future of Mars exploration that has progressed to the point of looking for biosignatures, the ability to cache samples for sample return, and planning for future humans to Mars. To tell us more about the latest science results, I'll turn the microphone over to the lead author of the science paper, Ray Arvidson.
Thanks, Michael. If we go to the first slide step, I want to reiterate something that Michael said. And our science results to be published tomorrow could not have been accomplished without the joint use of orbital and landed assets. And in particular, the first slide step will be a view from orbit, and it shows HiRISE, which is an exquisite color imager. And in addition to using HiRISE, we also used CRISM. And that's the hyperspectral infrared spectrometer that Michael mentioned, but we used it in a special way, in which we oversampled the acquisition of data in the long track direction. That's a form of super resolution, and it allowed us to detect outcrops with these clay mineral signatures that we couldn't do heretofore. And that's what we're seeing. In the lower left, that little red splotch are the very few pixels where we see this clay mineral called an iron smectite. Doesn't mean much to many people, but to geologists it's pretty exciting because it's a clay mineral that forms in a particular aqueous environment or water environment. And it's much less acidic and much less oxidizing than the Burns Formation sandstones, the sulfate-rich sandstones that Opportunity explored for most of its mission until August 2011 when it drove onto Cape York, which is an isolated rim segment of this very, very old crater called Endeavour, 22,000 meters across. And the white lines that you see drawn on the central image, those are locations that we visited with Opportunity and made measurements to really understand, kind of getting down in the dirt and in the rocks to understand the geologic setting and the details of these occurrences, the presence of this iron clay mineral called a smectite. So we go to the next slide step. This is really a neat area because it's very small. We couldn't have identified it otherwise than using the super resolution technique. And importantly, these are the oldest rocks we've seen because it's that tan kind of corridor that runs from left to right in the image. And these rocks are actually older than the Endeavour impact event because the ejecta sits on top of them. Copper Cliff, which you can see now, is impact material from Endeavour. So we're looking at rocks that in fact are older. And those things called the dark veneers, that maps 1-to-1 with where CRISM is seeing the iron clay mineral smectite. These probably formed in fractures, bedding for plane fractures, probably formed as ferrous smectite, oxidized later to ferric smectite. And the point is, these waters couldn't be too acidic and they couldn't be too oxidizing, or we wouldn't have produced these materials that we see. But it gets better, because we also saw fractures cutting through these finely layered rocks, and Esperance is one of those fractures. It's kind of bright relative to the surroundings, and it really is a place in which the composition suggests even more alteration. What you're looking at now on the next slide step is some of the veneers, these dark veneers, probably bedding plane deposits carrying the iron smectite, this iron clay mineral. A little bit of alteration, a little bit of water, a little bit of salt, mild conditions in terms of the water chemistry. Rather different than the younger Burns Formation, very acidic, very oxidizing conditions. The older you look, the better it gets in terms of habitability at this location. We go to the next slide step. Now we're looking close up at this fracture system. We couldn't see this from CRISM. It's 2 centimeters across. And even with super resolution, we couldn't get down to that resolution. So we went up to this outcrop, this fracture, and ground into it with a little bit of grinding pads left on our rock abrasion tool. And if you go to the next slide, it's a triangular diagram. It's a geochemist's diagram. And it's a way to get at the types of materials present. Here's the punchline. If you look at the average Martian crust, which is kind of like the overall material we were looking at, and then you look at those yellow dots, those represent compositions for the material as we ground deeper and deeper into this fracture, all the way toward an aluminous clay, an aluminous smectite called a montmorillonite. That indicates significant leaching and removal of iron and other materials, and it had to be done under, at best, mildly acidic conditions and reducing, not oxidizing conditions. You know, if I were there back when this material was being emplaced and altered, and I had my summer house, this is where I would drill to get good drinking water. So the older you look, the better it gets. You know, Opportunity is still exploring, and Steve will tell you a lot in a few minutes about what's coming up. But in the meantime, I'll turn it over to John Callas, the project manager, to give a little bit of the engineering history and what's coming up for Opportunity.
Thanks very much, Ray. No one ever expected this, that after 10 years, a Mars exploration rover would continue to operate and operate productively on the surface of Mars. So let's remind ourselves where Opportunity has driven. Remember that the rover was designed for only 1 kilometer of odometry. That's like 0.6 of a mile. So may I have the traverse pan? So we landed in Eagle Crater and then drove a few hundred meters over to Endurance Crater. And after exploring Endurance Crater, we headed south and we drove several kilometers to the half-mile diameter Victoria Crater. And we spent almost a year exploring Victoria Crater. And then we decided, well, where do we go next? So we decided to more than double the already tremendous odometry on this vehicle and head to the very distant, giant Endeavour Crater. And that's what you see here in this animation. And we are now exploring the rim of that crater, and that's where we are today. But after 10 years, you know, Opportunity has driven 38.7 kilometers, you know, fantastically more than the 1 kilometer requirement. That's about 24 miles. We've survived more than 3,500 Martian days on the surface, and we've collected over 170,000 images. But, you know, it's not how long the rover has lasted or even how far it has driven, but the amount of scientific exploration and discovery that's been accomplished in that time. So after 10 years, Opportunity is still in very good health, and it's still, of course, very scientifically productive. Although the rover has some degraded components, the right front steering actuator is jammed and no longer steers. The right front wheel, the same wheel, also shows elevated wheel currents. The robotic arm has some arthritis to it, and 2 of the scientific instruments no longer function. But in the past year, almost nothing has changed in terms of the health and status of the rover. It's been very stable. There is one recent issue that we're keeping an eye on. Opportunity had a senior moment. We call this an amnesia event. This has to do with the flash file system on the rover. This is the non-volatile memory inside the rover. Right now, it's not a health or safety issue. It's just an operational annoyance. But if it gets precipitously worse, there are some corrective actions that we can take to remedy this. As we approach the winter solstice, which is just 3 weeks away, the energy levels have improved on the rover. Airfall dust accumulates on the solar arrays, and that was what we originally thought would limit the life of this mission to 90 days. If I could have the next image. Opportunity has recently taken a selfie, if you will, a self-portrait using the cameras up here on the mast looking down. We've collected a color mosaic of several hundred frames, and you see that here, and you can see the dust on the solar arrays, and you can see how the rover is almost perfectly camouflaged against its environment. A few weeks ago, the dust factor, the performance of the solar arrays, was only about 47%. But recently, we've had some wind events that have cleaned some of the dust off the arrays, and so the performance is now at about 60%. This is higher than it has been for the last 2 Martian winters. This is good news. It means that we have ample power through the winter and that the rover can remain active and that we can drive pretty much almost every day and continue the exploration throughout the winter season. So with the arrival at Endeavour Crater, Opportunity has gone back in time, back to the oldest epoch on Mars. This creates some of the most scientifically interesting opportunities of the entire mission, considering that we're 3,500 days on the surface. But in addition to these tremendous scientific achievements and discoveries of the past decade, these rovers, both Spirit and Opportunity, have given us a great intangible, something different, something special. Over the past decade, through these rovers, our species have gone to work on Mars. And now a generation has grown up with these rovers and have been inspired by them. And some of those people are working on this mission today, are working on Mars. So in addition to being Earthlings, because of these rovers, we have become Martians too, dual citizens, if you will. We now live in a larger world, a world that extends beyond our own home planet. These rovers have made Mars our neighborhood and our backyard, and this is something truly remarkable. So let me hand it over to Steve Squyres, who will tell us something about the current science and the future science. Steve?
Thank you, John. Well, at a time like this, 10 years in, you start to think a lot about the legacy of the mission. And John has already talked a little bit about the cultural legacy. Let me say a few quick words about the scientific legacy. And I'd like to start with our first picture with the other rover, our blue-collar rover, if you will, the hardworking Spirit rover. Spirit landed on what turned out to be a vast plain of basaltic lava that was not what we went to Mars to find. But over a period of hundreds of Martian days, we climbed with Spirit to the summit of a hill. We named it Husband Hill. Rick Husband was the commander of the Columbia when it went down. And we named it to honor him. And from the summit of Husband Hill, in the picture that you just saw, you can look to the south, and you can look to the region where Spirit made two of its most important discoveries. As we descended down Husband Hill, we encountered a suite of outcrops that sort of looked different from the other stuff we'd seen before. And what we discovered after we analyzed the data from these outcrops, which we named Comanche, in detail, was that they were made largely of carbonate rocks. They were about 30+% magnesium and iron carbonates. One of the big mysteries on Mars has always been what happened. We know it was warmer and wetter in the past, but it's cold and dry today, and something changed. And one of the ways that you can make the climate of Mars change is if you had a dense atmosphere of carbon dioxide in the past, a greenhouse effect, and then the atmosphere goes away. Some of that atmosphere was surely lost to space, but we've always sort of suspected that some of it may have been locked up in carbonate rocks on the surface, because you can take carbon dioxide from the atmosphere and you can sequester it, you can hide it, if you will, at the surface in carbonate rocks. And so finding massive carbonates was a really major part of that story. Then as we proceeded south from Comanche, we went to a place where we ended up spending several years with Spirit that we named Home Plate. And Home Plate had many interesting characteristics, but one of the most fascinating was that we found very, very high concentrations, more than 90% pure, silica. This is not quartz, this is not beach sand, this was opal, like the gemstone kind of. And these are the kind of deposits that you typically find on Earth in hydrothermal systems, hot springs or volcanic steam vents. And so this was evidence of a hydrothermal system which would have been a habitable environment on Mars at one point in the past. The next graphic shows some of the wonderful rocks that we looked at with the Opportunity rover. This is at Victoria Crater, which John Callas mentioned, and it shows this stack of layered sedimentary rocks. When we landed with Opportunity, nobody had ever seen layered sedimentary rocks up close on Mars before. We were able to investigate these in detail. We found compelling evidence that they were made largely of sulfate salts, the kind of thing that would form if sulfate-rich fluid water evaporated away. And then, of course, the famous blueberries. Michael Meyer mentioned that we found hematite deposits in the form of little round nodules in the rock that formed when the hematite precipitated from liquid water. So again, telling a compelling story of water and habitability at this site. And then, of course, when we got to Endeavour Crater, we found the marvelous results at Esperance, the clay minerals that Ray Arvidson talked about. Now I'd like to go on to the next graphic, and let's linger on this one a moment because this is worth looking at. This is a very strange pair of images. These are two images. They were taken 12 days apart, and this just happened. I mean, this is going on right now. This is where Opportunity is currently parked, and you can see 12 days apart, a rock just simply appeared in front of us. In fact, we've narrowed down the date of its appearance to about a 4-day period. This is strange. Now, we don't think that anything particularly exotic happened here. The most likely scenario, just uphill from this location, as we were driving on some bedrock, the Opportunity rover did a kind of a pirouette. We call it a turn in place, but drove in such a fashion that it would drag the right front wheel kind of chattering across the ground. And we think that in the process of that wheel moving across the ground, again, this is speculation at this point, that we kind of flicked it, kind of tiddly-winked it out of the ground, and that it moved to the location where we see it. We have not found the divot, the hole from which this thing popped out, but the reason for that, we think, is because the place where we believe it came from is currently blocked by the solar arrays. We can't actually see that spot. So soon we're going to maneuver so we can go searching for that spot. But what's interesting about this rock is a couple of things. It appears that it may have flipped itself upside down. And if that's the case, what we're seeing is we're seeing a surface, the underside of the rock in its original configuration, that hasn't seen the Martian atmosphere for perhaps billions of years. And so we're seeing stuff that we don't normally get to see. The rock is small. It is sort of white around the edge outside, and it's got kind of a weird deep red color. Not a Martian kind of red, but more a deep red color in the interior. It looks like a jelly donut. White around the outside, red in the middle. We've looked at it with our microscope. It's clearly a rock. We've looked at it with our compositional spectrometer, and we're seeing a strange composition different from anything we've seen before. There's a lot of sulfur in it, suggesting a lot of sulfate salts, which might have precipitated out beneath the surface, and in very high concentrations of manganese, more manganese than we've ever seen in a Martian rock, high concentration of magnesium. We're still working this out. We're making measurements right now. So this is an ongoing story of discovery. As I said, Mars keeps throwing new stuff at us, and it's these kind of unexpected discoveries that make this mission continue to be the exciting, fun thing that it is. The final picture that I'd like to show is one that we took a little while ago, but it shows where we're going next. We are currently, as some of the other presenters described, on the rim of Endeavour Crater, and what we're doing is we're climbing the ridge that you see in front of us. This is called Murray Ridge. It's named after the late Bruce Murray, former director of the Jet Propulsion Laboratory. And we are going to ascend this ridge, we hope, all the way to its summit, all the way to the highest point, a place called Cape Tribulation. Ray Arvidson mentioned how data from orbit showed us at Matievich Hill, where we found Esperance, a signature of clay minerals that you could kind of see from orbit, but it was weak. You could barely see it. Cape Tribulation, to the south of where we are, that's where the mother lode appears to be, as we call it. There are much higher concentrations, much larger expanse of these clay minerals, and what we're going to see, we don't know. We'll find out when we get there. So we have an exciting period of discoveries ahead of us, maybe some of the best science yet to come, and as long as the rover keeps going, we'll keep going. And with that, I will turn it back to Guy Webster.
Thanks, Steve. So we'll have time for some questions and answers. And for reporters in the room who have a question, please wait till you get the microphone to you and identify yourself and your news organization. And on the phone, reporters listening on the phone, if you would like to ask a question, hit *1 on your phone, and the operator will put you in the queue. We have several reporters listening around the country and further. So first, I'll check if there's any questions in the room from reporters. We're also, and instead we'll go to a question on the phone from the New York Times.
Oh, hi, it's Ken Chang. Thank you for taking my question. I guess my one question is, how long is it going to take to get to the top of Murray Ridge? And secondly, at this point, what is going to happen first? That opportunity will break down, or that NASA will turn it off because it doesn't have enough money?
Well, I'll tell you what, Ken, I'll try to answer the first part, and then I'll let my colleague from NASA headquarters answer the second part. I learned a long time ago not to try to predict how long it's going to take to do almost anything with these rovers, because you have unexpected stuff along the way. The jelly donut rock, we call it Pinnacle Island, that popped up in front of us unexpectedly. It's a real opportunity, and so we're taking our time to look at it. So I don't know, but the kind of distance that we need to traverse to get to the summit of Cape Tribulation is comparable to the distance that we needed to traverse to climb Husband Hill with Spirit. That took us 400 or 500 Martian days. So, you know, it's going to keep us busy, I would say, for the next year, probably 2 years.
In concerning whether or not the rover will be turned off, as you know, we have a process in planetary sciences where as you go into extended missions, they cost a certain amount of money, and you have to decide whether or not it's worth the money for the extended mission or whether or not it should be applied to a new mission. In the case of Mars, we have several missions that are still ongoing that are in the extended mission, and we have to weigh how much money we have versus what missions are being most productive. So what will happen is this spring, there'll be what's called a senior review in which all the missions in planetary science are reviewed to see which missions are worth the dollars that you have to spend on them to extend them. And so it's the process of the senior review that makes any recommendation in terms of which mission should go forward and which mission may get turned off. And frankly, from all the missions that we have, they're very productive, and it'd be a shame not to have enough to afford the continuation of those missions. But we'll see how that turns out when we get to the senior review.
Thanks, Michael. We have a question from Alan Boyle with MSNBC. Alan?
Hi, thank you for taking the question. A follow-up on that is, could you provide the latest estimate on how much it is costing to keep the Opportunity mission going a year? And I wondered if the panel had any thoughts. I know you could probably take all day to talk about the highlights of the last 10 years, but if there's one thing that you feel either is on the top of your list or really needs to have more attention paid to it, I thought I'd give you the opportunity to do that. Thank you.
Alan, this is John Callas. I'll take the first part of your question, and that it costs approximately $14 million per year to maintain the team and the pace of activity that we have on Opportunity today.
Does anybody want
And with respect to the greatest hits, Ray's probably a little too modest to mention it, but I think the paper on which he's lead author, the discovery of those clay deposits, Esperance, has got to rank right near the top. And that's what motivates us so strongly to continue this search for clay minerals. Esperance was invisible from orbit, and yet following the clay signature took us to that. If we follow the much stronger clay signature that lies to the south, we think that there are fantastic discoveries that may lie there. And so if you ask what merits more attention, I think it's that.
Steve, I forgot to tell you about some other small locations along the way that we just recently found.
Yep. We'll look at those too, Ray, I promise.
Lots to look at. I should mention to reporters, if you can direct your question to a specific panelists, that'll help since we're dealing with two locations here. And we have a question from Ken Kramer, I believe, with you, Universe Today.
Hi, thanks for taking my question, and congratulations on 10 years. I have a question for Ray and Steve. I wonder if you could talk a little bit more about the area where you are right now. You got the Chrysler measurements to direct you to the spot where you are because of the phyllosilicates, I believe. So could you talk about what you have found there with regard to the phyllosilicates and what you're planning to do? And also with regard to Cape Tribulation, do you have to climb back down in order to get there, or you just follow the ridge, or how do you get there? Thanks.
Steve, you want me to start on this?
Go ahead, Ray.
So we have super resolution CRISM data thanks to the CRISM team and the Mars Reconnaissance Orbiter, all the way from Cape York to Murray Ridge to the beginning of Cape Tribulation, and we expect to get additional data to cover Cape Tribulation. And we're seeing these small outcrops of aluminous and iron clays, these smectites, all along where they're in the sun-facing side, and they're large enough, and large only means a few tens of meters across. So we stopped at one location called Moreton Island, which I like very much, a very pretty area on Murray Ridge. And it's an impact breccia, but with a lot of matrix, a lot of very bright matrix. And we think that's probably the carrier of the aluminous clay mineral. But that's still work in progress. But we had to get to north-facing slopes. So we're in an area called Cook Haven, named after James Cook, who was the captain of the Endeavour ship. And we're in the process of beginning the winter campaign. But as John mentioned, there's enough solar energy to examine the strata in Cook Haven. And I suspect it's mainly impact breccia, although we might go down stratigraphically low enough to see these pre-existing rocks, but we haven't gotten there yet. So Ken, it's very much work in progress. And as we kind of traverse south when the spring season comes about, there are lots, as I just told Steve, there are lots of small areas where I'm going to suggest we stop and look around. But it's very much detective work. And we're using CRISM as the way to get at the mineralogy, and then kind of boots on the ground or wheels on the ground in terms of getting into the dirt, grinding in the rocks, and putting together the whole kind of story that makes the best sense. So Ken, it's work in progress.
Thanks, Ray.
And Ken, with respect to your second question and the route going forward, I think Cape Tribulation is well named. We expect some pretty significant trials and tribulations as we work our way up it. It's steep, it's extremely rugged. We haven't chosen the route yet, and we could descend and then come at it from a different direction, or we could just work our way up that ridge. And that's the decision that we're going to make going forward, because it's driven not just by finding the best route to get up Murray Ridge and Cape Tribulation, it's also, as Ray has reminded us, driven by the science that we can do along the way. So we're still working that.
Thanks, Steve. We have a question from a reporter, if I remember right, might have been here on landing night, Leo Enright from Irish TV.
Yes, indeed, Guy. 10 years ago, it seems like a long time. But if I may put a question to Ray and also perhaps to Steve, about it used to be follow the water. It now seems to be follow the phyllosilicates. So I'm wondering from Ray whether he really thinks now that this is almost a new mission, and whether all the focus now is on these phyllosilicates. And if I could also ask Steve for a broader picture. I mean, you had tremendous success with remote sensing, as Mike Meyer said. So I'm just wondering what lessons are to be learned now by the Europeans and the Americans, who are both planning new missions. Are there places now that you say they should go? Very political.
Well, Leo, let me take the first part. So the Burns Formation, which you know about, because you were here at the get-go, sulfate sandstones. So they probably formed when more or less neutral waters came up with ferrous iron and saw an oxidizing environment. It makes Fe+2 ferric iron, and that actually produces acid as soon as you begin to make sulfates. So it was a very oxidizing, very acidic environment. Phyllosilicates, on the other hand, and minerals are kind of keys to past geochemical conditions in terms of the waters. The phyllosilicates have to form in less extreme environments. So these minerals called smectites, the particular type of phyllosilicates, they're the types of phyllosilicates that you get when you weather basalt. But it can't be done in highly acidic, highly oxidizing conditions, or you get other kinds of minerals that we don't see. So these are indicators of where you would want to go for mild aqueous conditions. Still corrosive, but nothing like the very low pH, highly oxidizing stuff that we found in terms of formation on the Burns Formation. So yeah, we are hunting for phyllosilicates from orbit using the super resolution technique. And then what really is the payoff is getting opportunity to those sites to do the details. For example, on Matijević Hill, in the Matijević Formation, that's the topic of tomorrow's science paper, it was such a small outcrop and so poorly exposed vertically that we don't know the environment of deposition. So we're carrying, maybe they were lake beds, maybe they were volcanic ash deposits, maybe they represent ancient ejecta prior to Endeavour, but we didn't have enough exposure to really kind of get in and do what a geologist would do in the field, look for cross-bedding, for mud cracks, and other features that, together with the chemistry and mineralogy, would allow you to kind of back out the full story. There are outcrops when we go south that are large enough and also phyllosilicate or smectite bearing, where we hope to kind of catch up to what Curiosity has been able to do in Yellowknife Bay, where you could have the strata exposed and where you can really back out the environment of deposition in addition to the geochemical conditions that led to formation of the minerals that we're detecting.
And just to answer your second question briefly, I think the key takeaway message here is the incredible power of having orbital assets and mobile surface assets working at the same time. The science that we're getting from the orbiters is dramatically enhanced by the rovers. The science from the rovers is dramatically enhanced by the orbiters. And so working those two together is very, very valuable.
Thanks, Steve. We are getting some questions in from social media, and I think this one is probably directed to John. Has the surface radiation environment on Mars affected the rover in any way?
No, not really. The rovers were designed for the environment, for the radiation environment that they're finding. And so we haven't had any issues of radiation damage or radiation-related effects. We do have, we can see in the electronics and in the cameras, some effects of cosmic rays or solar wind particles, but they're not a health issue for the vehicle.
And another from followers on Ustream on the chat. How is Opportunity's file system holding up? Are the energy levels okay? I guess that's two different questions.
The file system, I assume they're referring to our flash memory. Maybe just take a moment to do a little explanation here. We use the same kind of non-volatile storage that your camera or your smartphone uses, that it retains the information after the power has been turned off. Those flash file or flash memory chips have a finite number of read-write cycles to them. You can actually wear them out. But they're designed such that you don't continually read-write in the same location. They kind of spread things out, or what they call duty cycle, or load leveling the use. But it is possible that in time that you do wear out a particular location. And we may be seeing that. We think we saw this with Spirit. We were able to correct it on Spirit by reformatting. And some of you may have had to do this yourselves with the flash card in your camera is not working properly, and you reformat the flash memory card and things are fine from there. So we might have to do something like that for Opportunity, but we'll wait and see. It's as I mentioned earlier, it's only an occasional annoyance right now. It's not a major issue yet. And then the other question was about the energy levels.
Yes.
Well, the good news is that we've had some dust cleaning events, and that the amount of dust on the solar arrays is less than it has been for the past couple of winters. And in 3 weeks, we'll get through the winter solstice, and so the sun will be higher in the sky. So the energy levels should be increasing, as you would expect, as you move into spring and summer. So our expectation is that we'll have robust power levels, through the next seasonal cycle for exploration.
Thanks, John. We have maybe one or two more on the social media. Reminder, if any reporters in the room have a question, we'll bring the mic to you. Please identify yourself and your news organization.
Ewa Gajewska-Blaisdell, Ekspres Wieczorny, Warsaw, Poland. Also entrepreneur and investor who started collaboration with City of Lompoc on creation of California Space Center. My question is of interest to our readers who like to look toward the future and very much value your gentlemen's accomplishments. Mr. Elon Musk and his SpaceX ultimate goal, as he shared with us recently, is to deploy us human beings to be present on Mars. What you are doing here creates an incredible vehicle which potentially can be used for making transportation possible should the mission to Mars be achievable. So if I may ask for your response to convey to our non-technical readers about how would you like your accomplishments, your vehicle technology to potentially be harnessed in, let's say, 5 years from now for this type of a purpose.
Thanks for your question, and I think I'll toss that one to Michael if he wants to, or anybody else who wants to.
Well, certainly NASA has the ultimate goal of having humans to Mars, and in fact, our missions now, when going to Mars, will have on board something that will help further our knowledge that will help future human exploration. And good examples of that are on the rover Curiosity. We have an instrument called RAD, which is measuring the radiation environment on the surface of Mars. So we know what the astronauts will have to guard against when they go exploring the surface. And we just finished a call of instruments for the 2020 rover, in fact, asking for ideas, technologies that will help future human exploration. So certainly, any mission going to Mars, we would love to be able to have NASA assets involved in furthering human exploration. And it's, in many ways, it's not very important whether or not it's from commercial space or it's from a NASA-headed mission itself. So I think the broad answer to that is yes.
Any more in the room here? We have Adam here in the front. Oh, yeah, coming across.
Hi, Adam Palisi, Los Angeles News Group. Ray, can you tell me again when these discoveries, such as the smectites, were made? And how does something that is only meant to last a couple of months, how exactly does it last 10 years and continue to make discoveries?
Well, let me answer the second one first. It's a well-made American vehicle. Do you mean when in calendar date we did the discoveries? So this began in 2012 and was pretty well wrapped up by last spring and summer in terms of the observations. And then we buttoned up and started driving across Botany Bay to get to Murray Ridge. And we've been doing Murray Ridge for quite a while. But science is a difficult process, and the data analysis, the super resolution processing is very, very tough. Because the way we operate CRISM, you're putting pixels all over the surface, and you have to reorganize them and regularize them. So it took a while to put that together, to be comfortable with what we were seeing, to direct the rover to get there. And then all the observations that we made during the walkabout and all the in situ observations took a long time to come to grips with what it was telling us about the history of Mars.
Let me just add to the second part of your question as to, how is it that these rovers have lasted so long? Well, they're a solar-powered mission, and the only previous solar-powered landed mission experience we had was with Pathfinder. And so we knew about the airfall dust, and the expectation was the dust would accumulate at a rate similar to Pathfinder, and so we sized the arrays to give us enough power to last at least 90 days. What we didn't expect was that the wind would blow the dust off the arrays. In fact, we thought that the wind would not blow the dust off the arrays because it might cling electrostatically to the surfaces. So this has been a tremendous benefit, that this periodic cleaning. We can't predict it. It seems to have some seasonal relationship, but it certainly has enabled the rovers to continue to generate power. And then the other aspect of this is that we have an operations team that has been very innovative in figuring out how to get these rovers to survive the cold, dark Martian winters. How we can preserve energy, continue to be productive, but operate these vehicles at much lower power levels than they were originally designed. And Ray is right. These are magnificently built machines. They're really wonderful.
The project manager is being humbled. These are excellent machines. They're well designed, they're well built, they're tested, and that's why they're still working.
So is this unique that something lasts this long past what was expected, or is this something that NASA missions and Endeavour see a lot?
It's very difficult to say. It's in the choice of being whether you'd rather be good or be lucky, choose being lucky. Yes, these are well designed, well built. But we don't know what the environment is like. I mean, the amazing thing is that these vehicles go through this deep temperature cycle every single day. The temperature change from night to day is greater than the temperature change from summer to winter. And so they're constantly fatigued by this. It's kind of like going from the Sahara Desert to Antarctica every single day without a change of clothing. And the fact that they've lasted so long really speaks to the quality of the workmanship, the extensive testing that went into these vehicles. But is this a general trend? Are all vehicles going to last as long? I don't think you could make that extrapolation.
A reminder to reporters on the phone, for a question, hit *1 and you'll be in the queue. And at the top of the queue right now is Pete Spots with the Christian Science Monitor. Can you hear us, Pete?
Yeah, I can. Can you hear me?
Yes.
Oh, great. Thanks for doing this. This may be for Ray or Steve, kind of a big picture Mars question. Last we had the latest from Curiosity at Gale Crater with flowing water and streams and maybe a lake and again relatively benign conditions of acidity and so forth. And now we have kind of a second similar data point on maybe a half a hemisphere or a hemisphere away, but from a different time period. What is this latest piece of research done in terms of kind of either confirming or building on or whatever the dominant models you folks have for the evolution of the climate and the environment on the planet?
Want me to take a swing at that one?
You do it, boss.
Yeah, sure. There's an emerging picture, I think, here that conditions on Mars changed from the earliest epoch of Martian history, when you had warmer conditions, wetter conditions, and a chemistry that was mostly dominated, the water chemistry dominated by a neutral pH. And then you progress through a period of diminishing water activity, increasing acidity. So less water, less coming to the surface, less flowing across the ground. What was more acid. And then for the last 3 billion years plus, very little water activity at all. Most of the activity on Mars in terms of habitability and water activity was concentrated in the first billion or so years, and then after that it's been pretty quiescent. So this is one of these things where you piece together a story bit by bit, clue by clue, over a period of what's turning out to be decades. But I think the rover data that we've accumulated, the rover data from Curiosity, which is again looking very far into the Martian past, and then global data sets, CRISM on the Mars Reconnaissance Orbiter is one example. There was a marvelous instrument called Omega on the European Mars Express that was one of the first to really show this pattern of phyllosilicates and clays in neutral pH early, and then more acidic conditions later on. And so it's a picture that continues to evolve, but I would say that general trend is hanging together pretty well.
I think that's true, Steve. And what we're doing now is trying to take the geochemical and the geological evidence, which continues to accumulate, and then bounce that against the folks who actually model whole planets in terms of the thermal evolution in the interior, volcanism and tectonics, and also the atmosphere, greenhouse gases and those kinds of things. So we put together a kind of a global view of the evolution of this planet. Importantly, a lot of the rocks that we've been investigating are very early in geologic time, as we've said, and that record's long, for the most part, gone on Earth. So we're able to look back through to very early in time with a pretty extensive record, because the rate of erosion and turnover of Mars has been a lot less than on Earth.
We have an interesting social media question. I think this one's for Steve. It's from William Shatner. And he'd like to know if you've ruled out Martian rock throwers in the case of the jelly donut.
I think Martian rock throwers are unlikely, though we'll keep our eyes open for those. We did actually have another scenario, which we're still thinking about. It's the smoking hole in the ground hypothesis, as I've called it. We cannot yet rule out the possibility with certainty that there wasn't a freshly formed impact crater nearby, and this is a piece of stuff that was thrown out by a small impact. But we think the most likely scenario is that rock wasn't thrown, it wasn't kicked out of a crater, it was flicked out with one of our wheels, and we're going to take a close look at that hypothesis just in the coming days.
Thanks very much. And one more from social media. This is about a comet called Siding Spring that will come near Mars later in 2014. And the question from social media, from Epic Cosmos on Twitter, asked, are there plans to study Comet Siding Springs when it comes near Mars? And maybe
Great
Michael
question. Yeah, I can take a quick swing at that from the opportunity perspective, and then we can I'll let Michael address the other missions as well. One of the things that we've learned with Opportunity and Spirit over the years is that we can see meteors streaking across the Martian sky from time to time. And so when Siding Springs does come by, if Opportunity is still alive and well, and if we have enough power to take images during the daytime, one of the things that we'll look for is meteors in the sky that might be the track of debris that's been shed by the comet as it has flown by Mars.
Yeah, Siding Spring poses a real interesting situation. Its closest approach to Mars, I think, is October 19th. And so there's two aspects to it. One is this comet is going to produce material that will come to the Martian atmosphere, and we are going to have our Martian assets looking to see what's happening in the Martian atmosphere. And certainly we even had a trial run of doing that with the Mars Reconnaissance Orbiter HiRISE, looking at the comet Ison. So that's going to be very exciting, having a meteor shower on Mars. We're also looking at it very hard because there's a little bit of a concern that if there are a sufficient number of particles and large enough, they actually may pose a hazard to our orbiting spacecraft. And so over the next half a year, we're going to be doing some observations beforehand to see how active this comet is going to be and what the particle size distribution is and what sort of spectacular show can we expect at Mars from this comet, and also look to see what hazard there might be presented by this comet.
Thanks, Michael. And one more quick question from Tracy Watson of USA Today.
Hi, could you talk a little bit about the hypotheses to explain why Mars climate changed so much? That'd be great if you could just review that a little bit. Thanks.
Oh, Steve, let me take this. Okay. This is the big question, and we don't have the answer kind of fully quantified or even qualitatively together, but let me give you my working hypothesis. We form Mars, and planets tend to form hot because they accrete, and that kinetic energy gets changed to heat. The core forms, and that generates even more heat. The core is liquid, it's rotating, we have a magnetic field. The magnetic field shields the solar wind from stripping the atmosphere, as does our magnetic field. Because it's hot, it's extensively degassing in terms of volcanism. Those are the right conditions to have an atmosphere where water can be sustained on the surface and the shallow subsurface. Mars is a smaller planet than Earth, so it's going to cool down faster. And one can imagine that as the magnetic field was kind of withering as the core froze, as volcanism was kind of on the wane, we moved from a pretty active planet in terms of volcanic activity and water being on the surface for some period of time, and certainly in the subsurface, shallow subsurface, to the cold, dry conditions that Steve talked about a few minutes ago. And the transition is interesting. That might be the Burns formation, these hydrated sulfates, because you can explain the Burns formation by having more or less neutral water coming up to the top of the atmosphere and interacting with an oxidizing atmosphere or ultraviolet radiation. That turns ferrous ions into ferric ions. It creates hydrogen, which can escape, but it also makes sulfates. And when you make sulfates, you release protons, acids. And that's going to produce this very acidic, very oxidizing set of conditions. And if you don't have a lot of liquid water, it really makes acidic conditions. So that might be the kind of last major gasp of kind of a fluvial lacustrine system for the planet. Now, I made all this up, right? Because it's a good story and it's a good working hypothesis. But in addition to habitability and life, we're trying to understand the global system and how it's evolved over time. And it's a good working hypothesis that, you know, if you invite us back a few years from now, we'll probably change it.
Okay, well, thanks very much for the reporters and the others watching the briefing today, and we're going to close it at this point. Thanks very much.